Okay, welcome everyone. I'm going to talk about stable matchings, about counting stable matchings. This is based on joint work with my co-author Dömötör Pálvölgyi, and let's jump right into it. Okay. So what is a stable matching? This is a concept that's probably familiar to all of us here, but let's make sure we're on the same page. All right, so I've got a set of elements grouped into two groups, these Star Wars characters. I've got those in the first column and those in the second column. Okay. And any way that I pair up those on the left with those on the right is a matching or a perfect matching. But we have a little bit more complex model here, and the model is the following. Each of the characters has the ranked order of preferences of the characters on the opposite side here. Okay, so Kylo Ren has this ranking of the characters on the right. Poe has this ranking of the characters on the right. And this character has this ranking of the characters on the left here. Okay, so everyone has their ranked order preferences of all characters from the opposite class there. And now I want to find a perfect matching that avoids the following scenario, what we call an unstable pair. Okay, so here's a perfect matching, right? We've matched up all the characters with a character from the opposite class here, but this has what's called an unstable pair. Okay, what's an unstable pair? That's a pair of characters from opposite classes that are not matched to each other. They're not married, say, but they prefer each other to their current partners, right? An unstable situation, indeed. So we call that an unstable pair. Okay. So to sort of undo that, we could flip those matchings there. And now at least one unstable pair has been eliminated, but perhaps we introduce a new unstable pair in doing that. Okay. So the first natural question here is, given a stable matching instance, so that's a set of characters in these two groups and their set of preferences, is there even a stable matching, right? Can we somehow avoid it? And the answer is no, we can't avoid it. The famous theorem of Gale and Shapley from '62 says that a stable matching always exists in one of these stable matching instances, right? That's the stable marriage theorem. Pretty important piece of work. Taught in any graph theory or a discrete optimization class, certainly. A fundamental theorem, has many applications in real life as well. Okay, so a natural question in combinatorics, in this case posed by Knuth, is if you have a stable matching instance with n men and n women, how many stable matchings are there? Gale and Shapley says there's one. How many are there in total? Or what's a bound on the number you can have? It depends, obviously, on the ordered preferences. Okay. A completely trivial upper bound on the number, Sm of n is the number of stable matchings in an instance, is n factorial, right? There's n factorial perfect matchings, so there's certainly no more than that many stable matchings. Of course, many of those matchings will have unstable pairs, so it should be less than n factorial in general. But how large is it? Irving and Leather in '86 gave a lower bound, an exponential lower bound of 2.28 to the n. This was only for certain values of n, but it was extended about 20 years ago to hold for all values of n, essentially. So 2.28 to the n, exponential lower bound. The trivial upper bound is super exponential, so it actually took some time to lower it. In 2011, it was dropped to n factorial over constant to the n, but this is still super exponential. And then just a few years ago, Carlin and others, in a paper they presented at FOCS, in fact, gave the first exponential upper bound, which is remarkable. I mean, this is after 60 years, essentially, of work on this problem. They gave an upper bound of 131,072 to the n. They discussed a little bit that this base of this exponent can be improved a little bit, but I think they said that it couldn't be massively improved using the methods in their paper. Okay. And what I want to talk about today is our work that improves this upper bound to 3.55 to the n. So still exponential. I mean, we can't go, obviously, the lower bound is exponential, but a smaller exponent. I mean, a smaller base of the exponent. Okay. I'm going to give now like a sketch of how the proof goes here, and then talk a little bit about sort of our main tool at the very end, if we have enough time for that. The Carlin and other paper has the same starting point as us, so we have the same starting point as them. And actually, the main technique in some sense goes back to Irving and Leather, who introduced this important object that we'll analyze. Okay, so that's where I'm going to start here. Okay, with something called the rotation poset. Okay, so imagine we start with a stable matching instance. right? We have two groups of n men and n women and their order preferences. And you can build this sort of natural, somewhat natural poset out of that setting here. And I don't want to describe this too much because we're not going to actually use this today. But I just want to emphasize that there's this poset hiding in the background. And what's the poset? It's made up of these things called rotations, which you can sort of guess from the notation here is a pair of men and a pair of women that somehow you can, switch around marriages to sort of improve the overall stable matching, okay? And improve how? Well, I don't want to go into details exactly, but the point is there's this rotation poset hiding in the background. And what's really important that Irving and Leather proved, this key fact, is that downsets in the rotation poset are in one-to-one correspondence with stable matchings in the corresponding stable matching instance. Okay, that's crucial because what it allows us to do is count downsets in this poset instead of counting stable matchings. Somehow that's easier. We can use the theory of posets and so on to count these. What are downsets? These are just downward close sets in the poset. Okay, containment being comparability. Okay, but the rotation poset is tough to deal with. It's complicated. Okay, so instead of dealing with that, we want to deal with a simpler poset called the tangled grid poset or a tangled grid poset. Okay, I've illustrated one here, but let me explain what that is. Okay, oh, before I do that, the key point about the tangled grid poset is that it contains the rotation poset. What does that mean? It means that we can count downsets in the tangled grid poset instead of downsets in the rotation poset. And the tangled grid poset is easier to deal with. How is it defined exactly? Well, it's composed of two chain decompositions. You can see them illustrated here. The blue chains are called M chains, and the orange chains are called W chains. And these chains have the following property that every blue chain intersects every orange chain in exactly one poset element. Okay, so you have this kind of grid-like structure. It's not quite a natural, just simple grid. If it were, this problem would be easier to solve. It does have some structure to it. But this is what it looks like. Okay, so you have these two chain decompositions. Another property of it is that all the chains will have n elements on them. Okay, that has to happen because of the way that it's defined by decompositions. Okay, so instead of counting stable matchings and instead of counting downsets in the rotation poset, we are going to count downsets in the tangled grid. And this is an easier problem, at least for our method. Okay. So let's talk about downsets in the tangled grid. Here's an illustration. Here's our tangled grid. And here's a downset illustrated in red here, right? You can see that this is indeed a downset. All the elements below this are included, right? Those below it on the blue poset are there. And on this, blue chain are there. Those below it on the orange chain are there. This element is also below it because you can just follow the steps here. So that's a downset there. Okay, there might be other hidden relations here, but that only, that doesn't change the picture. Okay. It turns out that we don't even have to count downsets. Those downsets can be encoded by the maximal intersections with each M chain or with each W chain. So what I've illustrated here is the intersection of this downset, the maximal intersection of this downset with each W chain. So the max element on this W chain here, this orange chain that's in the downset is marked there. With this chain, it's this element here. With this chain, it's this element here. And actually there's no intersection with this chain up here, okay? That causes some technical issues, but I'm not gonna talk about them and they can be resolved, okay? So each downset can be encoded by this information here. It can also be encoded on the blue chains instead of the orange chains. And in the paper, we actually encode it in both simultaneously, which is redundant, but makes computation easier. Okay, so now all we have to do is count the number of such encodings that are possible in a tangled grid, okay? And this immediately leads to this silly trivial bound of n+1 possibilities on every chain, and there are n chains, so you have n+1 to the n. The +1 is for the possibility of no intersection, okay? But this is the worse than the trivial bound on the number of stable matchings, n factorial, obviously, so we need to do much better than this, okay? So how do we do better than this? Well, we're going to take this sort of probabilistic entropy approach here, and I want you to think about the following. In the previous thing here, if I already knew that this red element was the max element on the orange chain here, then I know that the max element on the blue chain is not this element up here, right? So there aren't really n+1 choices at each step if I already have some previous information. And that's what I'm going to talk about here. Okay. So what I'm going to do is put the M chains, W chains in a random order, and I'm going to investigate them one at a time. When I investigate them, it reveals the max element of the downset on that chain. Okay. When I do that, it tells me elements on the currently examined chain that can't be max elements. Okay, let me illustrate. It makes it much easier to understand. Okay, so reveal the max element of a fixed downset D on the M chains and W chains one by one. Okay, let's suppose that currently we're examining the blue chain and we've already revealed a number of chains before it. Okay, and so we're going to estimate the number of possibilities for the max element on the maximum element of D on the next chain. The next chain in this instance is the blue chain. And suppose I've revealed 3 orange chains before it. Okay, any blue chains I've revealed before it, I'm going to ignore those. Okay, I'm not going to use that information. I'm just going to use that on the blue chain. Okay, so let's suppose this point here is the max element of D on the orange chain. What does this tell us? Well, this tells us in particular that that element up here is not the max element of D on the orange chain because it's above this one. And that means that element isn't the max on the blue chain either, nor are these above it. So revealing this tells me that those are not the max element on the blue chain. Okay. Now reveal the next one. Those are out. They're above it. They're not the max element. Now reveal another one. Suppose it was over here. That throws out this one below. This element can't be the max element on the blue chain because the max element is at least here, because certainly that's in the downset. Okay. And so now what we have is this green region here. Those are all the candidates for the maximum element of D on the blue chain. So we don't have n+1 possibilities. We have fewer, in this case, just 4. Okay. So I want to estimate that green region there at any step in this process, right? So we're revealing chains one by one by one. We arrive at our current chain and we have some information at hand and it tells us how big this green region is. Okay. Now, obviously, we're going to have to compute an expectation because it depends on the way things interact with each other, the chains, I mean, what their intersections are, and which chains have been revealed prior to it. Okay. So how do we figure out that expectation? It turns out we solved this related problem. And I'm just going to jump over this quickly, but this related problem is asking for, if I have I black points on a circle and there's a red point initially on the circle, I want to know what's the expected length of the interval that contains the red point there. Okay, that's my green dotted area on the previous one in this problem here. This is an upper bound on that. Okay, and with you sit down and do some computation, you find the log of the expectation of that quantity is this thing here. Okay, it's this this quantity here. It's just a counting problem that's actually kind of nice to do. Okay, so using that information, we can compute the log of the expectation of x. The expectation of x is the expected size of the interval. Okay, now there's a number of different ways in which that interval can occur. Some of it is based on the number of orange chains that are revealed before, but we also have to consider when the blue chain is revealed in relation to the other blue chains. Okay, and so the point is, this is computation. I don't want to exactly show how this is derived, but the quantity from the previous slide occurs right here, and we sum up over all possible values of I. This is recording at what point the blue chain itself was revealed. Okay, all the blue chains are eventually revealed. Okay, so this is an upper bound on that expectation for an individual blue chain. Okay, if you let n get large enough, you can estimate this with the following relatively simple integral. You can plug that guy into Wolfram and get this exact value here. And that infinite sum, fortunately, converges, right? You have a log k over k squared. This is going to converge, and it converges to like 1.2, a little bit more than 1.2. Okay, so that's the expectation of x here. Okay, now we apply our lemma, which is sort of a black box, and I'm not going to go into the full details of that. But our lemma says, hey, if you know the expected lengths of those intervals on each of the blue chains, then you actually have an upper bound on the number of total encodings. Okay, the number of different ways you can encode. Okay, so log of the number of encodings is bounded above by this expectation here. Pi is the permutation of the chains, so it's the order in which you've revealed them. And without explaining the notation, this log xj that's just this x here. Okay, there's a bit more notation that I don't want to define exactly here, and we have to sum this over all two n chains, right? So there's n orange chains and n blue chains. So you have to compute all of these. But the main lemma says the number of encodings is bounded above by this quantity. And we know the expectation of each of them individually is bounded by this constant, and there's 2n of them. So the log of the encodings is bounded above by this quantity. Well, that's easy enough. Just solve for encodings and you get about 11.11 to the n. Okay. All right, well, great. That's not quite the upper bound we claimed, but that is a relatively small exponential upper bound. Okay. So I haven't really said what the main lemma is, and I'll just say on this next slide, I'll just show it here because I don't quite have enough time. It's this relatively complicated lemma, but basically what it says is that we can estimate or bound the number of encodings here when we reveal components of an n-tuple one by one at random and estimate the number of possibilities at each reveal. Okay. If we have that information, then we can bound the size of S, which is a collection of n tuples, by this set of expectations, the sum, well, the expectation of the sum of these logs. Okay. Well, with linear expectation, you can bring that inside. And how do you prove this? It's actually very simple. You can prove it with simple information theory or just really manipulating the entropy of a random variable function. That's really proof 2 is an entire proof there. Okay. And so this is the main tool that we used. There are lemmas of this type already out there in the literature. This is sort of our version that we used for the paper to fit this problem. And this lemma appears to be applicable outside of this problem as well. Okay. Okay, so anyway, to wrap things up, I want to talk about that upper bound a little bit more here. How do you improve it, right? That was 11.11 to the n. How do you improve it to 3.55 to the n? What are the changes you have to make? Well, the overall structure is the same. You examine the tangled grid, you apply the lemma. Okay. But there's a few things you can do. The tangled grid actually inherits a little bit more structure than we claimed. Okay. So in fact, the M chains and W chains intersect in 2, not 1 elements. Okay. This means that previously revealed chains give a little more information than before because the intersection sizes are larger. Okay. The other piece of information is that we completely ignored any blue chain that was revealed before our current blue chain, but those actually give you information as well. Okay. So exploiting these two things together does eventually get you an upper bound of 3.55 to the n, okay? With quite a bit of technicalities. There's a lot of technical details to be worked out, but that's the rough idea. And we think further improvements to that are possible, with just more and more careful analysis and maybe inheriting a little bit more of the rotation poset structure. You can bring that bound down a little bit. But this method seems to not be able to bring us all the way down to the lower bound 2.28. That seems to be out of reach with this technique here. If that's even the truth, we don't know one way or another. But it doesn't seem like it can be pushed much further and certainly not close the gap. At least we don't believe. Okay. All right. So that does it. Thanks very much for your attention.